Okay, so I've started back the recording and let's continue. Hope you are back from your break. So as previous time, let's do some hands-on exercise. Let's do some coding and let's try to solve some problem with this finite element method on our own, not using any simulation software, any finite element software like ANSYS or Abacus, not using anything, just using this knowledge that we have just obtained, hopefully, try to apply it. So we are talking about the same problem of heat propagation. So we are going to need to have some numerical values, of course, for all things. And I put here some examples that I used here. You are not obliged to follow these values. And as usually, I highly recommend to vary the values and to consider different ones to see how they affect the solution. And one note right away about your assignment, that for your assignment, I will not be giving any exact numerical values. So it will be up to you to choose them. And I hope you will all choose slightly different values, which usually happens if you are not doing it together. Of course, it's not a problem if something coincides, some values still. Okay, and again, the recommendation is that to use values that you have some intuition about, like that you. Well, I understand that with heat flux, it might be a little bit tricky because usually in everyday life people don't deal with the heat flux values at all. They deal with displacements, they deal with forces somehow, at least with weights, but they don't deal with heat fluxes. So yeah, this is some kind of value of heat flux that you can get maybe from sun radiation. So not something extremely big and not something negligible. Okay, so we are going to use some mesh parameters. So how many elements we are going to have along y-axis and how many elements along x-axis. And total number of elements, obviously, since it's rectangular mesh, is the product of these two. Number of nodes is a little bit tiny bit tricky. So how to calculate the number of nodes in this kind of mesh? Well, it's not very sophisticated question. I think you're used to solving this kind of problems, so it will be number of elements plus 1 times number of elements in another direction plus 1. Okay, so I introduced parameters about the material, just one parameter in this case, conductivity. And this is something that is typical for a steel, like 45 watt per meter per Kelvin dimension. It's not millikelvin, it's meter times Kelvin. Okay, and heat flux dimensions is watt per, it's energy per area, energy per time per area. So the energy per time is watt, and per area is per square meters in SI system of units. Okay, so this is applied loads. This is a physical material property, then geometry of our domain, and parameters of our mesh. So that's all input information that we need. Then let's do this thing with this mesh. We need to somehow store this this mesh. So the information about elements and about nodes. We don't really need information to store elements as a separate array here. We only need actually coordinates of nodes and their numbers, right? So the way how I used in this study assignment, it's not the most general way, and it's not exactly how it's done, of course, in a commercial finite element software. But for this simple problem, I think it's one of the easiest way how we can implement this finite element mesh. So this is dx and dy. I use this notation. It's not differential. It's just dimensions of our elements in x and y dimensions. So they will be all the same in this simple examples. All elements are of the same dimensions. And those are our storage containers for coordinates of the nodes. So this is xk, this contains coordinates of all nodes in x direction, and this contains coordinates of all nodes in y direction. And then we kind of need this. So I tried to show this for this example, like 4 in a row and 3 elements in a column. This is the mesh that I will be using for this example. So we'll be explaining everything on this mesh, but of course we make it in a way that you can easily make larger number of elements and denser mesh therefore. So this is then black is numeration of elements that I will be keeping in mind, and red is numeration of nodes that I will be keeping in mind. Okay, quite straightforward. Of course, you can use different order of how you number nodes, but this is some simple example that we can come up with. And so in this loop, I make this nlog matrix, which essentially describes me which node numbers belong to which element. So like this element number 6, it includes nodes 7, 8, 13, and 12. And if we look at it here, element number 6, it's 7, 8, 13, 12 in this order. Okay, I think it's not the most computationally efficient way to do this, because I use the dimension of my nlog array. It changes on every iteration of this loop, which is usually not very much recommended in programming. But so of course we could have reserved proper space for it beforehand here, but it's not really essential for understanding the method. So of course you can do this code more efficient computationally. But in this case, I just add this row on each iteration.
Like the special thing for nx equals 4 and ny equals 3 before loop.
What do you mean?
That's this loop, especially log, keeping that this was only apply for n y equals 3 and nx.
No, not really. Why not? You can use different numbers. So you just put them there here, nx and ny, the number of elements in x and y direction. And they don't have to be 3 and 4 like they are here in this example. So this should work.
But I wouldn't need to adjust the log. The log currently only has 4.
Yeah, but this is because, okay, so this 4 is not because of our dimensions. This 4 is because each element includes 4 nodes, has 4 nodes. This is about type of our elements. So this nlog is always going to have 4 columns until we are considering this type of elements with 4 nodes. So this is not universal in terms in the sense that you cannot apply this, that it only applies for this kind of element that is shown here. It won't work for element with 8 nodes. Of course, you will need to modify that. The principle will still stand, but how you can do that, but yeah. But then this all those nx and ny, they reflect the number of rows in this array. And you can use different, but you will have different. In this case, you have 12 because it's 3 by 4, because we use 3 and 4 here, but it may be different. Okay, so we need somehow to store this information about elements and nodes and their numbers and their locations. So these 2 things keep our locations of nodes, and this nlog array keeps kind of correspondence of node to element correspondence matrix. So the row number is a number of element, and in each column you get a number of nodes which belong to this element in certain positions in this order. Okay, can we move further? Okay, I suppose we can, otherwise please let me know. So this is what we did. So about the mesh. So now let's think about boundary conditions a little bit. So the boundary conditions are reflected in this right-hand side of our algebraic equations, this f vector, and this is how it is calculated as we mentioned. So our shape functions are here. So let's say let me remind you what we want to have. We want to have prescribed Q0 on this side and prescribed QB on that side. And how I can put them into this right-hand side of this equation into F. So this, according to this expression here, right? So how do we do that? So shape functions, we do know them. So this is the first time I introduce this transition between local and global coordinates. So okay, let's start with the left-hand boundary. So with this one, and then by analogy I will make for the top one. So in this boundary, we have nodes which differ in position along y only. So I made this in a little bit simplified way only for y only. So we have one of the elements which is which belongs to this boundary. So these two nodes, T1 and T4, they, let's say, belong to this boundary, and we need to apply something there. Okay, so this is a left boundary, which means is that psi coordinate is equal to -1 for both nodes. Nodes which psi equal to +1, we don't consider in this boundary condition. Okay, so then we calculate this integral. So let's say we have extracted those nodes. Okay, we kind of do that manually in this case. So we calculate this integral. This Q0 is applied to heat flux value, then transpose matrix of shape functions, and I only take those that correspond to our nodes. This integral gives me just Q0 value, integral over eta from -1 to 1. So I integrate from here to here. So along this boundary, I don't integrate, it's not integral across the element area, it's integral along the boundary. And we only use part of the element which corresponds to this boundary that is on the left-hand side. So we only need to integrate from here to here, nothing more. That's why I can use only one integral along eta here from -1 to 1, and I put this thing here, and I apply this extraction of nodes. So it's already nodal shape functions, and I only apply that to those that which are here, which will my first and last. So in other words, I put coordinate psi equal to -1, which cancels out my other values. Okay, because these are n2 equals to 0, and this equals to, so these two equal to 0 for this coordinate, and these two degenerate to this form. So I applied this psi -1, which is essentially that I picked only these two nodes. And calculating this integral gives me this value. So this has been done in local variables. So I need to do this transition. And this transition is done with the Jacobian determinant of the Jacobian of this transformation. And in this case, I only need to care about one coordinate because only I have integral along eta coordinate. So the ratio between the derivative of global coordinate y with respect to local coordinate eta is just how the dimensions according to the dimension of the element, and 2 because it's from -1 to +1. So it's just dy by 2. Correct? No objections? So this is, then I put this finally here. This determinant it should be under this integral. So in this case, we can factor it out from the integral because it doesn't depend on coordinate. Dy is not differential, it's my dimension. Okay, and this is what we obtain for this kind of element. So the local contribution to this global right-hand side vector from element number E looks like that. So physically or mechanically, I don't know, it corresponds to the values of two values applied to these two nodes, this one and this one. And if you look at those values, they are made as a value of the heat flux times half of the length of the element in this direction. So overall, I'm applying Q0 heat flux on this whole side. And heat flux is its energy per time and per area. So to calculate energy, I need to multiply it by the length of this side in 2 dimensions. So therefore, it's multiplied by d1, and they are just distributed evenly between 2 nodes. Essentially, what I do here with this linear interpolation. So it's dy over 2 and over 2 here. So this Q0 times dy will be whole energy per time applied to this coming through this boundary, and then I divide it by 2, and these are my contributions for each node. So it's that simple as that. You will have to deal with it a little bit more in your home assignment. I will hopefully have time to explain that later. Okay, so then let's put it into our code. So the way I did it, so this is our boundary conditions as we described, and we need to apply them to these left-hand side nodes. So first I made quite in a quite straightforward way those flags for which indicate where I apply these left-hand side boundary conditions and for which nodes or elements I apply this top boundary condition. So those are just my internal variables which indicate that it's a flag that for this element I need to apply this boundary condition, and for this element I need to apply this, and for element in the corner I obviously need to apply both from here and from here. Okay, so those are just my flags to identify geometry location of elements. And then for these left-hand side elements, we just have this local contribution from each element in this form. And then I sum over all elements and I position them correspondingly, and I get this total. Then I have another contribution from this top boundary condition. It also goes to the right-hand side. Where else could it go? So the difference is that we have now heat flux QB, and it's located for 2 different nodes, for nodes 3 and 4, right? So therefore it comes into positions 3 and 4 in this local vector of heat flux coming from a certain element and from this top boundary condition. Okay, I'm not sure it's the most elegant way to do this thing, but I think it's not very sophisticated, at least, and easy to understand. how it works. And then I need to identify nodes on this right-hand side where I apply my essential boundary condition, prescribe the temperature. Okay, you can do that in a number of different ways, of course, but essentially I need to have these nodes as an array where I identify this boundary condition. So is it all right there, or let me see nodes? Okay, so what I did here, I did not prescribe this boundary condition. So I identified nodes where I want to have essential boundary condition, prescribed temperature, identified elements where I need to have natural boundary condition because they are coming from, they kind of applies to elements. Eventually, it all transforms to nodal contributions in our in these vectors, right? But I need to, it's more convenient to think about elements, I suppose. And how these contributions look for in terms of from each element, contributions from boundary conditions, how they look in terms of nodal contributions of heat flux.
This is the first one you put for PE equal 1 x 7.7u, and for top one you didn't put the step.
So what is the difference? So I didn't hear maybe. Yeah, I can.
Yeah. Here and use the just let's say in the summary here I just did the and didn't for the visual and it should be NY instead of NY.
Yes. So
The first initial one, then double points, then NY, then ends with an NA.
let me check 1 second. So yeah, the question is why it's written differently.
Yeah.
Well, no specific reasons. Yeah, yeah, probably I should have written it in a
One goes
similar way.
it's for increment by nx. By the top row, we only need to increment by 1 because we start at the element 9 and then go 10, 11, 12. Okay.
Yeah, so okay, should we go further? Good. So this is the part that I like the most because it's quite universal, and this is exactly how it is even in more difficult situations. So this local conductivity matrix, we discussed how we can calculate it in this simple case of rectangular elements using just this d parameter with aspect ratio of our elements. And nothing really sophisticated here. I just put directly this thing into the matrix, and then I use this factor multiplier, right? K over 6d. Well, maybe this is not the most part that I like. Maybe the next one, how we combine it into the entire matrix. Yeah, because this is quite simple, I suppose. Once we've calculated it, of course. So yeah, here maybe I should make a comment here that in this simple case, and that will be the case for your assignment as well. So we can just easily analytically calculate components of this matrix. But in practice, how it's done for general case finite element analysis, it might be not that simple. And what's used instead is used numerical integration that I think you have studied in this course before my contribution, and this Gauss integration. So this is exactly what is used to calculate elements of these matrix in general case in finite element analysis, at least in commercial finite element codes. And then you might hear such things about such thing as integration points with respect to finite element methods. And people are saying that originally in stress analysis, we have stresses not at nodes, but at integration points, and then they are extrapolated to nodes. And that is true. And basically what the reason is that you can, while you are calculating components of this matrix numerically using this Gauss integration, you already calculate values of some matrices, those B matrices, gradient matrices, at corresponding locations. And you can store them, those values, and use them later to get stresses out of nodal displacements that we will get if we would get if we were solving the deformation problem. Okay, so this aspect, how this matrix is calculated, is done differently in more general case. But in this real case, it doesn't really worth trouble. I suppose we can just put this very simple matrix result of simple integration here. And this is how it appears to be for our case with its 4x4 matrix, right? Again, dimensions of this matrix is not about how many elements we have in our mesh. It's about the nature of the element. And we have element with 4 degrees of freedom, namely temperatures at 4 nodes. So therefore, this matrix is bound to be 4x4 in the heat propagation problems using this kind of elements. So this will be always the same for this problem, regardless of what are your mesh parameters, how many elements you are using. Yeah, but again, it's usually not done this in this analytical ways in more advanced, let's say, calculations, or let's say more universal when you're trying to make a more universal code. And you kind of can share resources, because with this approach, once we can calculate this matrix analytically, but then when we finish with our solution, we find nodal temperatures. We still might want to find, for instance, heat fluxes within elements, and for that we would need to calculate those B matrices for elements again for some coordinates, and we might not need that might not have needed that if we had calculated this matrix nummerically and had stored those matrices at integration points. But this is some kind of computational aspect. So if you are done with this matrix, just put it there. No big deal, I think. No. What kind of error?
Array and it must be positive integers or logical values.
Yes, they must be. Why are you using logical variables in your? So what is the variables? You are using also this d, which is and what is the value of d? Okay. And what else? Where can this logical thing can come from? There is nothing else in this matrix. Only d.
You in the same line.
Let's try to
do it starts with this.
So like you need to be nice.
I always try to like do it up. It doesn't matter. There's something here, but I'm not sure what. But it's the same things like here already. So.
Maybe make it without this.
That I already tried that.
Yeah. That makes it the same. Some difference somewhere that looks like. Okay, can you maybe try to remove parts of this? Like,
I have no idea. I want to try. Just short.
Okay. So this is what in the it's brackets. There is no symbol multiplication.
And then same variant. So I don't like it. Minus.
Just minus. Yeah.
No, that's
Okay. But it works out. Okay. Okay, it's nice when you get an error from the code, but it's more difficult to find a mistake when you get results, but they're just not right, which happens, of course, a lot. Okay, so let's go further. So now this is maybe interesting thing that we need to construct this global matrix out of local matrices. So basically, with this numeration that we have, so we just use those. Okay, how should I explain this? But so it might be not obvious why I did it this way exactly, and it's not the only way you can do it. So I mean that for this selected numeration that we used, so this is the right matrix that we must obtain. But how exactly I made this composition of these loops? Of course, you can do it a little bit differently.
inside the element?
Yes. Yes. So I use explicitly for everywhere because it only works because other things anyways work only for nodes that we used previously. So I make a loop, three loops, and this is the main line that makes composition of this matrix. So what is below this is about the right hand side, how we compose contributions from different elements to the right-hand side. I think this is quite straightforward in this case. So we just place it into corresponding position, which is identified by this index 0, 1. And index 0, 2 we use for horizontal positioning of the fragment of the element stiffness matrix in the global stiffness matrix. So basically what I'm doing here, I use two indices, int 0, 1 and int 0, 2, for positioning vertically and horizontally element stiffness matrix in the global stiffness matrix. And that is defined by the by both number of our element and number of node at which we are looking at, right? And I use this nlog matrix, which provides me numbers of nodes for each element. And okay, so let me maybe run roughly over it, so to give an idea of why it is done this way. So first I have this outer loop over all elements. So for each element, I want to place its local matrix into some place in the global matrix. And the same applies for right-hand side, but it's a bit easier, so I maybe don't even mention about it, so only focus on this part. So this is outer loop over all elements. Then within each element, we do two loops over its nodes. And I need those two loops to identify both horizontal and vertical position of each component of this local matrix. So I add this G and K. So I'm going over horizontal axis and over vertical axis in my local matrix. So these are JJ and KK variables loops. So they're going like this and like that from 1 to 4 within local matrix. And this II identified me number of elements overall, where I should place this overall. And then these are components of my matrix, and those two variables, index 1 and index 2, they identify where exactly in X and Y direction I put this particular component of local matrix into global matrix. Okay, again, I'm not sure this is the most elegant way or the most computationally efficient way to do that, but it gives me exactly the result that I want to have for this numeration of nodes, like according to rows. So this works only for this kind of numeration where of elements and nodes, row by row. Okay, if you use something else, then you will need to change this approach accordingly. And what I want to you to be aware of, that usually commercial software does something else after that. So it does something like that, but then it makes a renumeration of nodes in order to obtain the most efficient form of this matrix. So the form of this matrix, so where exactly those elements are positions, will depend on how you numbered your nodes, like row by row, like I did here, or some other way. And the general property of this matrix, it's kind of band structure. So there is a band from left top corner to bottom right corner of non-zero elements going like here. And then there are zeros in top right-hand side and top right side and bottom left side. So it's only some band of non-zero elements. And by changing your numeration appropriately, you can sometimes even make this band narrower. And the narrower is this band, is the the more effectively you can solve this system of algebraic equations numerically then. So this comes into the domain of mathematical methods, how to solve numerically those systems of equations, because it's solved numerically. Eventually, it's not solved analytically. Nobody calculates inverse matrix or something like that in for real situations. So the codes, they usually do this renumeration after this has been formed with boundary conditions. Okay, but we are not going to do that. The matrix is quite all right for us. There are some zero elements inside, but we don't really care very much about computational efficiency. Okay, well, more or less last hard element that we need to do. So we made this right-hand side, and we made this, I don't show it here, but we might, and we made this global matrix. And then the thing that is left is essential boundary conditions. So far, our matrices and our right-hand side don't know anything about this side where we want temperature to be specified, essential boundary conditions. And the reason for that is that they are not included in our variational form. And therefore they are called essential. We need to work on them separately. And that's, in this case, there are, I think I put here zero temperature, right? Yep. Okay, so let me keep back for 1 second. I want to show that I made one simplification. I did not pronounce it explicitly. So with respect to the statement that we used earlier, I used zero temperature on the right-hand side. Not some prescribed value T0, but just zero, like absolute zero in our case. It's a bit annoying simplification because it makes this much less universal. But this is something that allows us to get rid of one computational procedure at all. So it makes this thing quite easier. It's not very difficult to make it for other values, but it requires additional step, and I don't think we really need to spend time on that today. So, and for this case, when it's homogeneous boundary condition, when zero is applied, what I can do is exactly, I can cross out all rows and all columns in my mass matrix, which correspond to the position numbers of nodes where I want those essential boundary conditions to be applied, and only put zeros everywhere in those rows and columns, and only put unity at the intersections of corresponding rows and columns. Because why we can do that? Because this matrix will be multiplied by the global vector of nodal coordinates. And when I'm multiplying it, so it's row by column. So for each row of this matrix will correspond to some component in the result vector. Right? The result are heat fluxes. And what we need to specify that for certain temperatures, for certain nodes, the temperature is already predefined and is equal to zero. So this product of this line row from this matrix multiplied by the column of our nodal temperatures must give a zero for the specified nodes. And so it doesn't really matter what are elements in this matrix, in this row and in this column. It only matters that I keep this intersection. Then the product of this line by this column will give me exactly the temperature at this particular node that I am interested in contribution. And then I make it zero by putting zero in the right-hand side in the corresponding line. That's quite well, it takes some abstract thinking, a little bit, imagination. but I tried to make it as simple as possible for this example, because if there are non-zero, then it requires some manipulation with the entire matrix at all. So it's not difficult to code it, but it's a little bit more difficult to grasp this idea. I think it's a bit easier to see with this. So I want to specify that like t something, what was it? Like t5 at number 5 is equal to 0. And t5 is here. Like this matrix will be multiplied by a column of all values, and on the fifth position, let's say it's fifth position, doesn't really matter. So there is t5. Well, yeah, it is fifth position in my enumeration. And this t5 is equal to 0. And this says that since it's always 0, then the contribution of fifth column of my matrix will always result to 0. So I don't need this column at all. Like for any other temperature, for any like when I'm multiplying like first line from this matrix by this column, so this element will be multiplied by my fifth temperature. And this fifth temperature is 0, so I essentially put it here. The result of this product will be 0. So I can keep 0 here. Okay, and same stands for the rows. So fifth must be 0. The only thing that I need to keep not equal to 0 is this 1 at the intersection of the fifth column and fifth line, because then this product of fifth line by this column gives me just t5. And if I have 0 in the right-hand side, this is exactly t5 equal to 0. Yeah, of course, yeah. Otherwise, it would be how is it called? So this matrix with 0 determinant. I forgot the term, but yeah. So then we cannot solve it. At least we cannot find a unique solution in that case. Okay, and that's it. And then we're good to solve it. Just use this solve algebraic equations command, and we can make some nice visualization quite easily with MATLAB using this contour f function, which gives me something like that. This is my initial mesh 4 by 3, and I had to reshape a little bit results in order to fit this from our original column in order to the dimensions of this space that coordinates of with our nodes, x locations and y locations of nodes, right. So because the contour f command it makes a correspondence between those locations and values, and we can easily do that using this reshape command. So reshape those resulting nodal temperatures into this matrix with corresponding dimensions. And then I can make this nice plot. And I can look at the results, and I can check whether they make sense or not so much. So what I can see, I remember that I have some value of heat flux applied from here. So it's coming in, positive value. So I see that there is a higher temperatures by this area, which makes sense. I prescribe 0 boundary condition, essential boundary condition, 0 temperature on the right side, and yeah, it looks like it's maintained. Well, then with this top boundary, there was a outflow of heat, right? There was negative heat flux coming in it, so there was heat coming out. So we can see that it's a bit lower. So it also makes sense. Of course, we cannot compare it numerically, probably with just our intuition using those values of heat flux, but we can at least make this qualitative assessment. And one other thing that I want you to pay attention to is that this bottom side. So there was this insulation boundary condition. Insulation boundary condition in thermal analysis means symmetry. So this picture is supposed to be symmetric with respect to this line, so we can make a reflection from it. And for that reason, those lines, which are isothermal lines, so lines of constant temperature, they must be perpendicular to this line, right? And we don't see it really with this initial 4x3 mesh. So this doesn't look perpendicular, this line, to this bottom line. But this is just our approximation error. If we change the number of elements, and this is the picture that I made for 80 by 40 elements, we can see that now we can really see that those lines are really coming into this lower boundary at the 90-degree angle, how it is supposed to be for insulation boundary condition. So now I can see that it's really maintained this boundary condition. So this might be not really enough mesh for analyzing distribution of temperature in this problem, but this is most likely enough already. Okay, does it work for everybody or no? Okay.
I get the inverse thing, and my numbers are all minus.
What is minus?
The number I this is the graph. This for the K matrix at least was the same when I looked at it previously.
But the other boundary, right-hand side, is it the same? Do I show it somewhere here? No, I don't show.
Same. This matrix combines with mine perfectly.
Okay, so you did exactly the same with the right-hand side. Yeah, probably I should have put it here for comparison also, the right-hand side. But
if you go to the next one, it's like the same.
Yeah, but I don't show the right-hand side here. So what is it? What would it be? So okay, but can you look into results like this T vector? Yeah, let's say like temperatures at those left nodes. We will see if it's visualization or this. Like, can you look at positions number 5, 10, 15, and 12 in your. Okay, let's what is F? So let's have a look at nodes number what those 1 and 6. What do you have there?
I don't know what F is. But for me, is that it's minus or something.
So yeah, so this Q0 is 500 and QB minus 300. Or did you use something else?
Yeah, not the same. It's just where to define it.
Okay, and then you did this. So I wanted to check if you have the same, but you have negative. Yeah, then it makes sense that it's opposite, looks opposite way. So maybe here in this contribution you did something else. What could be different? So in the right hand side, if you look at so this is my right hand side at nodes, well, at let's say first element in the right hand side in the F. What do you have there? Is it positive or negative? First.
Yeah.
Why is it 0? It should be this value, I think. The first element of F. Okay. Can I ask online participants, did you get these results?
I got it like other way.
Also another way.
Yeah. I add that picture on the chat.
I'm getting some kind of warning that the matrix is singular.
Okay, so we had this problem with one of participants in class about having inverse picture, and I think there was something in the right hand side, so we have fixed it. So can you look at the first element, like the top, the number one element in the right hand side in this F column? Was it Pauli who said that it was inverse?
Yeah.
Can you look and say me what is the value there?
Do you mean which?
Well, so you are making this F vector. So the F1 element, what is it equal to?
I can show it. So that's the values on F.
Where is the chat? I'm trying to look at your picture. Okay.
Yeah. And next one is the F array.
Okay, so I see it.
Yeah.
Okay, so there are some negative elements in your.
Yeah.
Well.
We have the first one is 83, not 62.
And you now got the same picture. Okay, so but other elements, do they look the same?
No, it's 83. Then on the 6, it's 166. Also on 5, he only has 25. It should be 0.
Yeah, 5 should be 0 because of this. Yeah.
Something wrong.
F. Yeah. So this modification.
I think for the second one, we should look into the for loop because it means the 5 hits applied at around 10, and the other one has wrong value.
So probably looks like you have some wrong values, at least in this right hand side F. Yeah, that's my oversight. I should have put it here for comparison. But yeah, so it's at least it says that it at nodes on the right side, you specifically apply here that it must be 0, and one of those nodes is number 5, right? And so, and it's not 0 in your case at node number 5. So this is node number 5. So I think you have some mistake maybe with this right boundary condition nodes. What do you think? What is your array, this right BC nodes? Does it contain 5, 10, 15, and 12? Oh, not 12, 20.
4, 8, 12, 16, and 20. So yeah.
Yeah, so you are applying 0 temperature at some different nodes.
Yep. Yeah.
You should check this one. Okay, so can I help somebody else who has problems somehow? I obviously cannot check all the codes right now online from anybody, but if somebody has some mistake that he doesn't understand where could be the origin, some error that it's not clear where it can come from, let me know. I will try to at least point you to the direction where to look at. At least in class we did this the same way, obtain the same results. Okay, so what I suggest, so yeah, obviously there might be some mistakes in different codes, and that's perfectly normal. And yeah, maybe we don't spend, because we are running a bit out of time, maybe we don't spend our time now to correct all of them, and you do that on your own. You're gonna have these slides a little bit later. So yeah, also you can always write me an email if you want to get a personal advice about something that worries you and you don't understand how to deal with in these codes or in your assignments later. So now I want to give you a couple of words about your assignment. So can you please listen a little bit? So this is the description of your assignment. So this is the same problem that we dealt with during previous class. This stretching of a bar under force applied at the edge, and also body force, non-uniform body force applied somewhere in the bar. So this is what we solved with finite difference methods. And what I want you to do is to solve this using finite element method as well. So it's kind of more easier thing that two-dimensional problem that we did from the perspective of finite element method itself, those stiffness matrices and so on, combining all stuff together. But one element that is new here that we did not deal with today is this right-hand side, how to incorporate body force in it. So I want to give you will have these slides with some hints about that, but I want to give you some comments how to do that, what it takes. So, but first, what I want from you as a result, I want from you a report and your MATLAB code. So that's the bottom line. So you submit on Moodle. There will be assignment on Moodle. I don't have access there right now, but I will, as soon as I get it, I will put there the assignment. So you submit there your MATLAB code and your report. And I want the report to be self-explanatory, so that I only will go into the code if there is something wrong with the report and it's not clear where is the error coming from. So the code is more like for more deeper checking if something is worrying you or me in your report. But the report itself should include, so I tried to put here the description because previous years I was getting reports of looking very differently. So what I want there to be, I don't specify how exactly it should look, but it should include the description of problem that you are solving. Like we are solving this problem with a bar, the approach that you are using, like what kind of solution did you come up with in parts where you had some freedom, and what numerical parameters you chose. Then I want you to provide in the report results for load cases in form of plots, like displacement versus coordinate plots. For load cases, the first load case is there is no body force, so only the force applied at the end. You're gonna get linear distribution, of course. The second case is just for checking. The second is for uniform body force, so it has the same value everywhere along the bar. And the third is linearly increasing to the end. And the third is maybe the most tricky one, this head type function for the body force distribution over X. But we look at them previous time in our finite different course, so it shouldn't be completely new to you. And then once you do that, or maybe at the same time, it doesn't really matter, I want you to compare your results with results for the same four load cases obtained with a finite difference scheme that we worked on last time. It's nice if you put, for instance, in a single plot, you put curves for both methods, and we can see visually if they are deviating much or not, and where exactly. But also, I want you to make some kind of numerical comparison. So the maximum deviation is, I don't know, 2% for this mesh, and for that mesh is 0.1%. So some kind of analysis from your side about how different are the solution, what is the reason of difference, and so on. And those main things I want you to put into conclusions, and I put exclamation mark here because quite often students don't pay really much attention to this thing. So it's not you, yeah, it's the typo, it's your, should be, I forgot the R symbol, sorry for that. So I want you to make some minimal conclusions, not and try to use it like to reflect on the problem, that what you have learned and how did you like some things, what about the method. So this method, for instance, provides better accuracy for if I use only 2 elements discretization. But if I use 12 elements, another one provides more accurate solution. If you have this feeling about which one is more accurate, because you don't have a probably analytical solution, well, you still can obtain it for those tricky cases with non-uniform body force, but I don't ask you to do that necessarily. So what do you think about results? Are they different? Are they the same? Are the linear equations exactly the same? Because you notice that each of those methods provides you, leads you to a system of linear equations eventually. And provided that you are using the same number of elements discretization, I want you to think about, are those linear equations exactly the same or not? And in which case they are. So some spoiler that they will be exactly the same for some cases, but not exactly the same for others. I mean, from those 4 considered load cases. So try to think about these 2 methods using this example and this comparison that you made. So this is what I want you to do, this report, and provide your code as support, like in case I need to dig into it. And I want to have all elements. So to receive the maximum grade, which is 5, you need to have all these things included in your report. If you are missing, if something is missing, and even if it's absolutely correct, but you just did not consider 2 of those load cases, so it cannot be maximum grade, as you might understand. So in case you have some, I'll discuss with Greg and confirm with him. I think it will be 2 weeks deadline, but well, I will discuss with Greg and we'll put that on. Yeah, it's normally 2 weeks, so it will be by default 2 weeks deadline. If you have some problems and you need a little bit more time, you're always free to write me in email, and it's okay to ask for an extension if you have some more pressing issues at the moment, but you want to get maximum grade, and it's okay. I can be flexible in that regard. Okay, so this is formal about how it should go and how it will be graded. So basically all components are present in the report and no major mistakes. Of course, there are could be some smaller ones. Then this is maximum grade. If something is missing or there are some fundamental mistakes in how you did in your results, then it will be not maximum, depending on how much is missing and how deep are mistakes. So starting by basically from lower in the extreme case to second to the maximum one, which is 4. Okay, so some hints that you will have this on Moodle, so don't try, no need to remember that. So this is the variational formulation for this variational form for this problem. Okay, so it includes this force. It comes in this funny way without integral here, but because it's one-dimensional form, there would be integral over the boundary, but there is not, since we have only one point at the boundary. So it comes in this funny way. It's a natural boundary condition, this applied force in this case.
And this is the object not in 2-dimensional, but only in x direction.
Yeah. Yeah, exactly. So we don't have second dimension. Otherwise, there would be integral over some dimension along the boundary. So generally, it comes as integral over the boundary where it's applied. So you don't need to think how to do that, and it includes body force here in this integral. And this is some mathematical things about finite element methods. So you are encouraged to do that on your own, but to check some key steps about matrices, element stiffness matrices, and Jacobian of coordinate transformation, and how it looks like in general, this system of linear equations, you can reference to this slide. Yeah, I hope I didn't make any typos here, but let me know if I did. I hope not. And one thing that might be a bit difficult here in comparison to what we did in class is how to incorporate this body force. So it comes into this variational form as an integral, and therefore in the right-hand side you have this integral in this form. So this is the value of the body force, and this is shape function. So you have to calculate integral over the element of the body force multiplied by shape functions, vector of shape functions. And so if this body force depends on the coordinate, then you really need to do some integrating. In this case, if it's linear, and it's not more than linear in your assignment, it's piecewise linear always. So you can use this. You can use the same shape functions that you used for approximation of the known variable. You can use them to approximate your body force within your element using nodal coordinate, using nodal values of this body force, F1 and F2. And in case if it's linear, and in your case it is, then it's exact representation. In other cases, it would be approximate. Okay, so I calculated this integral for you. It's no big deal, but for you to have a reference and to check. And it's not very, not absolutely obvious, maybe, the result. So what we see here is that each element within which the body force is acting. So let's say we have F1 and F2 values of the body force at the nodes of this element. And then it provides contribution to the global force right-hand side vector in this form. So at one node is 2/3 of this value at one node, and plus 1/3 of the value at another node. So this is here. And on the second part is different. 1/3 of first and 2/3 of second. So this is the contribution of the body force from this element to nodes, like in terms of nodal forces. Those are nodal forces. Okay, and these values F1 and F2, you know that you know them once you assumed some specific distribution of body force along your bar. So it changes from something to something, and you can easily calculate at each node what is the value at each node, and those will be these values. And for each element, they will be a little bit different. And then you put that into that. Okay, and since we are super late, I'm sorry, but if you have still maybe 1 minute, yeah, I think that's it for my presentation. But I wanted you to make a super short quiz, like feedback. It doesn't require writing anything, just grading different parts of this class. Where is it? Different parts of this class from 1 to 10. So this is this presentation. Reflection, it's anonymous again, of course, has nothing to do with your grades and so on. The reason and you must be able to do it on your own. There is just one slide with questions. I don't want to put it here, so to not confuse anybody. So I will not know who graded in which way. And the reason I'm asking for that is there are two basically reasons. So one is that we've been incorporating this fragment of 2 classes into this course on computational methods and mechanics for already a couple of years. And we think it fits well, but what really matters is not what we think, but your opinion on that. So it would be valuable for me to understand how you find these topics and these problems that we considered how valuable in this particular course and for you in general. And another, of course, is for me. Like me, I want to be a good teacher, and if I would like to know your honest opinion about different aspects of this class, how happy you were with it, and on which I should work on. Okay. With this, I will probably stop the recording.